Welcome to The Explainer. If you've ever heard that quantum computers are both 0 and 1 at the same time and just felt like something was missing, like that can't be the whole story, well, you're in the right place. Today, we're going to skip the usual analogies and look at the actual math, the real engine that makes these things tick.
So, how can a computer be both 0 and 1 at the same time? I mean, we've all heard this line a million times, right? It's kind of the classic intro to the whole world of quantum computing. But if you're anything like me, you've probably found that this analogy, well, it's catchy for sure, but it doesn't really give you that satisfying aha moment. It almost raises more questions than it answers.
And you know what? That's because the real secret, the actual mechanism behind all this quantum magic, it isn't hiding in some clever analogy or wordplay. Nope. The answer is in the math. To really, truly get how it works, we have to learn to speak its language. And that's exactly what we're going to do right now. Okay, so here's how we're going to tackle this. We're going to build it all up step by step. First, we'll talk about why we have to go beyond simple zeros and ones. Then, we'll get into the language of phase. After that, we'll cover states and operations. Then we'll put it all together to really assemble the idea of a qubit. And finally, the payoff, we'll see how a quantum computer can solve a real problem faster. Sound good? Let's go.
All right, Section 1, Beyond Zeros and Ones. So, to really appreciate what's so special about the quantum world, we first got to be super clear on what makes it so fundamentally different from the computers sitting on our desks.
And really, the fundamental difference starts right here. A classical bit, the kind in your phone or laptop, it's just a simple switch. It's either off, a 0, or it's on, a 1. That's it. It's definitive. But a quantum bit, a qubit, well, its state is this combination, this blend of both 0 and 1, all described by probabilities until the very moment we measure it. So the big question is, how do we actually describe this much richer, more complex state? Well, for that, we need our first essential tool. And this is something you might remember from math class: complex numbers. This is the language of what we call phase.
And it all kicks off with this little thing called the imaginary number I. Now what is it? It's just the square root of -1. Think about it. On a normal number line, you can't square any number and get a negative, right? A negative times a negative is a positive. So mathematicians basically said, well, what if we just invented a number to solve this? And that's I. And by doing that, they literally opened up a whole new dimension for math.
So what happens when you take a regular, old, real number and add an imaginary number to it? You get what's called a complex number. And here's where the magic really happens. When you plot it, it's not just a dot on a number line anymore. It becomes a point, or even better, an arrow, a vector, on a two-dimensional plane. And that arrow, it has a length and it has an angle. And trust me, that angle is going to be absolutely crucial. And this is exactly why that angle matters so much. In quantum computing, we almost always use complex numbers in their exponential form, because when we change that angle, what we call theta, we're not just moving a point, we are rotating it around a circle. This rotation, that's what physicists call phase. It's not just on or off, 0 or 1. It's about which way the qubit is pointing in this abstract space. It's one of the secret ingredients to a qubit's power.
Okay, so complex numbers give us a language to describe the rich state of a qubit. That's tool number 1. But we also need a way to actually change that state, to manipulate it. And for that, we bring in our second major tool, linear algebra. So, how do we use it? Well, we start by representing our basic quantum states as vectors. We say the 0 state is just the column vector 1, 0, and the 1 state is the column vector 0, 1. I know it might seem a little abstract right now, but trust me, giving our states a concrete mathematical form like this is the foundation for everything that comes next.
Okay, so if our states are vectors, what actually changes them? Well, in the quantum world, these operations are called gates. And what are gates, mathematically? They're just matrices. You can literally think of a matrix as a little transformation machine. You put a vector in one side, the machine does its thing, and a new transformed vector comes out the other side.
And the process of actually applying a gate is, believe it or not, pretty straightforward. It's just matrix multiplication. You take the matrix that represents the gate, you take the vector that represents the qubit's current state, you multiply them together, and bam! You get the vector for the qubit's new state. It's that simple.
Okay, let's take a breath. We've got our tools now, right? We have complex numbers to describe phase, and we have linear algebra for states and operations. Now it's time to assemble the qubit.
Let's combine these tools and really see the math behind that famous property, superposition.
And here it is. This equation is the heart of quantum computing. A qubit's state isn't just the 0 vector, and it isn't just the 1 vector. It's a linear combination of both. You have some amount, alpha, of the 0 state plus some amount, beta, of the 1 state. This is superposition in mathematical terms. And guess what alpha and beta are? They're our old friends, the complex numbers.
So what do alpha and beta actually do? They control the probabilities. See, when we finally measure the qubit, all that quantum weirdness stops, and it has to choose to be either a 0 or a 1. The chance that we'll find a 0 is basically the size of alpha squared, and the chance we'll find a 1 is the size of beta squared. Before we look, it's a world of possibilities. The moment we look, it snaps to a single, definite reality.
Okay, but you might be thinking, how does a qubit even get into this superposition state to begin with? And that's a great question. It doesn't just happen on its own. We have to use a special operation, a specific matrix, called the Hadamard gate. You can think of the Hadamard gate as the on-ramp to superposition. It takes a simple 0 or 1 and puts it into that perfect 50-50 mix.
All right, now for the payoff. We've built up all these mathematical tools, so let's actually see them do something cool. We're going to walk through a really classic example. It's called Deutsch's algorithm, and it's a perfect demonstration of how all this math creates a true quantum advantage.
So here's the puzzle. Imagine you're given a function. It's a black box, meaning you can feed it an input and it gives you an output, but you have no idea how it works on the inside. All you know is it takes a single bit, a 0 or a 1, and spits out a single bit. Your job is to figure out, is this function constant, meaning it always gives the same answer no matter what you put in? Or is it balanced, meaning it gives different answers for different inputs?
Now, for a simple 1-bit function like this, there are really only 4 possibilities. You can have 2 constant types, one that always outputs 0 and one that always outputs 1. And you can have 2 balanced types, where the outputs are mixed. Our entire job is just to figure out which of those 2 categories our mystery function belongs to.
Now, if you were using a regular classical computer, how would you solve this? Well, you don't really have a choice. You have to test it twice. First, you'd plug in a 0 and see what you get, but that's not enough information, so you'd have to run it a second time, plugging in a 1. Only after 2 separate queries can you be 100% sure what kind of function it is.
But a quantum computer, it needs just one, a single query. That's it. It gets the answer in one shot. And that is the quantum advantage. And the reason it can do this is by using all the math, superposition, phase, all of it that we've just been talking about.
So how on earth does that work? Well, here's the recipe. First, you prepare a qubit in that perfect superposition state using a Hadamard gate. Then, and this is the genius part, you query the function just once, but you do it on this superposition state. Because the qubit is both 0 times and 1, the function basically runs on both inputs simultaneously. Then, you apply another Hadamard gate and you measure the qubit. And the result of that single measurement tells you with absolute certainty whether the function was constant or balanced. It's incredible.
And that right there, that's the core principle of quantum advantage. By processing multiple possibilities all at the same time, quantum computers can find solutions in one step that would take classical computers many, many steps to figure out. It just makes you wonder, doesn't it? What other problems we once thought were completely impossible, might this new kind of thinking finally unlock?